Rajesh, are we starting?
Yes, sir. Yes, sir.
Unmute, madam. Ask to unmute.
Yes, good afternoon, all.
Yes.
I welcome all for this online seminar on astronomical data, sources and analysis. Now I request our beloved principal, Dr. L.D. Horkeri, sir, to welcome this the seminar. Now over to Horkeri, sir.
Hello. Hello.
You are audible, sir.
Audible?
Yes, yes, sir. Yes, sir.
Yes. Good afternoon to one and all present over this online seminar. On behalf of our college physics department, we are organizing a national level online seminar on astronomical data, sources and analysis. So on this auspicious occasion, I mean, a very much fascinating occasion of astronomical data. That is, astronomy is a very interesting topic out of physics. So on this important occasion, we are very much having with us Dr. Priya Hassan, Assistant Professor in Physics, Maulana Azad, National Urdu University, Hyderabad. So on behalf of our college staff, students and all, I extend a warm and sincere welcome to Dr. Priya Hassan, madam. Welcome you, madam. Welcome you.
Thank you, sir.
Welcome you. Yes, welcome you, madam. Yes, at the same time, I extend a warm and sincere welcome to all the faculty who have joined this online seminar. And I extend a sincere welcome to all my dear colleagues, dear students, and faculty from different institutions and delegates from different colleges. So we have joined this online seminar. So once again, I extend a warm and sincere welcome to one and all present over this seminar. Thank you. Thanks a lot.
Thank you, sir. Thank you so much for welcoming the audience and the participant and madam. Now I request our respected the head of the Department of Physics, Dr. P.R. Jirgal, sir, to introduce the today's resource person, Dr. Priya Hassan, madam. Over to sir. Sir, welcome, sir.
I, Dr. P.R. Jirga, head of the Department of Physics, Jabin Science College, Department of Physics. I would like to introduce the resource person of today's national level seminar on astronomical data, sources and analysis. That is Dr. Priya Hassan. Dr. Priya Hassan is an assistant professor in physics at Maulana Azad National Urdu University, Hyderabad, India. She did her integrated masters from the Moscow State University, Moscow, Russia. There is a PhD at Osmania University, Hyderabad in 2004 and postdoctoral research in France and IUCAA, Pune. He was awarded the Woman Scientist Award by DST in 2006. She has presented her work in various conferences in India, Europe, and US, and in the United Nations, Vienna. Her research interests are in observational astronomy, star formation, star clusters, and galaxies. She is actively involved in Olympiads, public outreach, and science popularization programs, and has worked on various projects with the AU, OAD, that is the US Consulate, Hyderabad, etc. She is the co-chair of the Women in Astronomy, WGIAU, and a member of the Public Outreach and Education Committee, Astronomical Society of India, and ISD, DT, TMT. And that is with this brief introduction, that is I'm going to present before you, that is a unique resource person for today's national seminar to you all. That is a thank you, Pandito.
Thank you very much, sir. Thank you, sir, for the kind introduction.
Thank you, sir.
Thank you, madam. Thank you, sir. Thank you, sir. Now I request Arvind Kulkarni, sir, to speak some words about this.
Yeah. Yes, I'm just taking about half a minute from Dr. Priya's time. I just want to inform all the students that you are extremely lucky in having a very resourceful person at this seminar. We have tried many, but then we found this person to be extremely useful for our purpose to introduce observational astronomy and data analysis. And I want you to pay attention fully and attend and take the benefit of her vast experience as well as interest and deep connection to teaching. A person may be an expert, but the deep connection to teaching and interest in teaching the younger generation is not a very common phenomenon among our community of teachers. But here is a person who is extremely concerned with the learning by the younger generation. So I hand over him. Please listen carefully. Thank you.
Thank you, sir. Thank you, Arvind, sir, for your kind words. And thank you very much, Jabin College, for having invited me to give this talk. Thank you very much. So I shall just share my screen and I'm sorry. I hope you all can see my screen, astronomical data sources and analysis. Is that clear?
Yes, madam. Yes, madam.
Okay, fine. Okay, fine. So then I'll go ahead. So good afternoon, everyone. And I will be talking to you about astronomical data, sources and analysis, because as Arvind sir told me that a lot of students are actually looking for projects which they can do, or even faculty members. And I'd be basically talking briefly about how could you be doing projects. Obviously, each project would take a lot of time to describe in detail. So there's a limitation to how much I can cover just now. But I hope that in this session, I should at least give you the basic information that you would need if you want to actually go ahead with some kind of data analysis. So yeah. So let us look at what is astronomical data. We know that in present times, astronomical data is all in the form of digital data, right? We have it all in the form of soft copies, digital data, and this involves in astronomy, for example, there are basically two types of data which we have. Either you have in-depth study of individual objects, where you look at a targeted object for a long time and you in-depth try to study that object, or the other option is when you are actually doing a survey. So in astronomy, what we sometimes do is you actually do a survey where you try to study the complete sky. Okay. With that, you get the whole sample of the whole sky. But obviously, there's a trade-off in this, because either if you actually do in-depth, right, then you can give longer exposure times, you can observe for a longer time, but obviously you cannot observe the whole sky. And on the other hand, if you want to observe the whole sky, then you cannot observe it for very long, right? So there's a problem of depth. So if you're doing it in a form of a survey, it is what we call shallow. You cannot go too deep inside, because of the simple reason that in this case, the problem is that when you're looking at it, the time which you have, you cannot look at it for too long, right? And therefore, that's the problem that we have, that you actually have to, either you go in for an in-depth thing of a single object, or what you can do is you can actually do a shallow survey of the whole thing, right? You have one of the two options. You cannot do both. And that's the issue which we have with astronomical data, because either you look at targeted for a single object for a long time, or you can actually look at a shallow survey of the whole area, right? So you have to have this trade-off which we have between the two options, right? Now, because of this kind of thing, there's a lot of astronomical data now available on the internet. And for example, we won't talk about this in detail, but there's a Vista survey, which gives you about 150 terabytes per year. Or for example, there's going to be a new survey, which is called the LSST survey, which would give 500 terabytes a month. Similarly, there are many simulations which have even more, they even have petabytes, a very large amount of data. And therefore, to house this data, you have specific data centers where all this data is stored and kept literally on hard disks, right? And then one can actually access this data via the internet. So you have many data centers from which you can actually collect the data of different objects. Now, you can actually analyze this data using certain tools which we call virtual observatory tools, which are tools in which you do not need to do any coding. Or you could actually have Jupyter notebooks where using in Python is a software language, you can actually use Python to actually, analyze the data. Now, what is the type of data which we have in astronomy? So one kind of data which we have in astronomy is what we call images. You can have images, and somebody says there's a problem with the WhatsApp window in my browser. Is there a problem? Hello? No, I don't.
Madam.
Okay, fine. So there are the different kinds of data which I've listed over here. What are the different kinds of data which we have? So one kind of data is actual images, right? The other kind of data are catalogs. So catalogs are in the form of tables where you have, your object, say the brightness, various parameters about that object. And then you have another object. So those are catalogs where you have a list of different things for which you are listing things. You could have also something which is called spectra. What do we do in spectra is that you just take the light from an object in a very small wavelength range and you break it up into the wavelengths, right? Which is like looking at the rainbow, right? You're actually getting your VIBGYOR. So in that way, that is what is called the spectra, where you're actually looking at the VIBGYOR or the spectra. And importance of spectra is you will know the brightness of the source in different wavelengths, which, as we are all students of physics, you know that is related to the black body properties of the body, right? So if you actually have a plot or an understanding of what is the intensity over different wavelengths, you will have an understanding of the black body spectrum of that object. You could also have data in the form of what are called time series data. By time series data, you mean to say is that supposing you have a source which is changing with time. So you actually have the brightness of the source at different times and you tabulate that. So that is what we'd call a time series data, where you have the different brightnesses of the source in time. Okay. There could also be what is called polarization data, which is specifically if you look at the light which you're getting through and polarize it, then you will get different polarization properties of the object and accordingly look at the polarization. Oh, sorry, I think I was muted, right? I was muted for some time. Hello?
No, madam, it is audible.
It's audible. Okay, very good. Okay, so the first kind of data which we'll talk about are images, right? What are images? So images, when we talk about digital images, right? Digital images, these are basically, it's like a two-dimensional array, okay? Where at every point, you have these squares, right? This is an XY grid or a two-dimensional array. And at each point, you have some brightness, right? And that would be the pixel value. The pixel means a picture element, okay? That's what is called a pixel. So if this is a 2D grid, you can have a small square, which is basically the brightness at that point, right? And using this, we can actually create, I'll show you how to create RBG, which is, red, blue, green colored images. How do you actually produce colored images and how this is related to wavelength or the energy of the source, right? So, but this is about a basic.
Madam,
Yeah.
you are muted.
Yeah, now I'm unmuted. When I was pressing the space bar, it's muting. Okay. Now, if you look at, thank you, sir. So if you look at images, you could have images of either what are called point sources or what are called extended sources, right? So for example, if you're looking at a star, that would be a point source. If you look at a galaxy, that will be an extended source, right? And to look at these objects, what was developed it would be interesting for you to know that this was basically developed for the Hubble Space Telescope. When the Hubble Space Telescope was launched in 1995, at that time the requirement was to find a source with which you could actually get digital images. And that's when CCDs are what are called charged coupled devices. Okay, these are the source through which you actually get digital images. Okay, and what are CCDs? I'll tell you. So what are CCDs are basically, it's like, again, it's an array, right? But it's like an array of buckets. Okay, so what you basically have is you are looking at some object, and depending on the brightness of the object, a different amount of photons will fall at different points. And based on that, you will have some amount of count, some photon count coming at different points of this object, right? And then through the electronics, the amount of electrons which are caught at different points are actually collected and they are forwarded, and that is what is called a CCD. So a CCD is the source of getting digital images. And how do we get RGB or red, blue, green colored images? Is that in the CCD, you actually have pixels, some which are sensitive to red light, some to blue light, and some to green light. So you know blue light is shorter wavelengths, red light is longer wavelengths, green is in between. So you'll have different pixels which are sensitive to different lights, right? And with that, you will have different counts coming over here. So you, for example, if you have a filter over here, a red filter, when the light passes through the red filter, you will get some counts coming at different points. When it passes through the green filter, you will get some points. And when it passes through a blue filter, it will go through some points. And then all these three images are added together to actually give you what is called a colored image, right? And this is exactly the principle which is used on your cell phones, in digital cameras, in camcorders, in scanners. All these objects actually use these kind of filters to actually get this. So when you actually look at astronomy images, here I have two examples of astronomy images. What you can see is that what is done is basically they actually take images of the object in different filters. So filters in succession. So for example, you take an image in the red filter, in the blue filter, and then in the green filter, in all the three filters. And then you add those images together to get what are called RGB images, or red, green, blue images, right? So you can combine them all together by getting these individual images, right? In some cases, which I will show you, astronomy images, we also add artificial colors, because in principle, like I told you, what the CCD gives you is actually a black and white image, right? We artificially add color to it by adding whatever filters we want, right? But sometimes in certain cases, we actually add artificial colors, which I will also show to you now very soon. And astronomy images are kept in a format. You all must be aware of PNG format, JPEG format, GIF format. There are different formats in which images are stored. But specifically for astronomy, we have a format which is exclusively for astronomy, which is called the FITS format, which is the Flexible Image Transport System. I can see there's already a question from Harshavardhan. Why are there more green color sensors? That's a good question. That's basically because if you actually, Harshavardhan, you were asking me, why are there more green colored sensors? Like I told you, blue light is shorter wavelength, red light is a longer wavelength, but green is in between. And therefore, if you want to sample a source, the chances of the photons being in the in-between wavelength range is more possible, rather than for them to be in blue or for them to be in red. And therefore, what you see in this grid is, you can see 50% of the squares are actually green, because that will actually catch all the in-between wavelengths. And then the blue one will catch the longer ones, and the red one will catch the blue one will catch the shorter ones, and the red one will catch the longer ones. So what happens is, since the green is in between, it will permit photons which are of in between wavelengths, right? And most of the photons are going to be of in between wavelengths. So that I can catch all the photons, it's better for me to have more green filters, because the bulk of the photons will all fall in this range compared to this or compared to this. Like you can see in this image itself, you can see many more green squares than red or blue, right? So that's basically because it's the so that's why we are opting for that, right? So like I was telling you, I was telling you about the FITS format. The FITS format is the format exclusively for astronomy images. So when you'll actually see astronomy images, you will notice this format .fits, right? Like you see .jpeg or .png, you will now see .fits format, okay? And this is a specific way in which the data is kept so that you have the pixel values of all the data. Along with the data, you could also have a header file which has information about the image, in the sense which telescope was it taken from, how many pixels, what was the exposure time, what was the filter. So there's a lot of additional information which is packed along with the image, which comes in FITS format. And therefore, the FITS format is considered the most desirable form in which you can actually have astronomy images. And note that we will talk a little bit about image processing, the different ways in which you can deal with the images. And most of them, to do the image processing, you need that your images should be in FITS format so that you can do some amount of image processing. Now, just as a repetition, I was trying to tell you what are images that are, I'm sorry, the resolution has got spoiled. But for example, here you have a picture of Abraham Lincoln. And if you were to actually pixelate it, you zoom it so that at every point you get squares, right? Because these pixels are basically squares. So you keep zooming it till you get these things. Then each square will have a certain count. So if you look over here, you can see here, this is the number 14, this is 134 or something like that. So you can see that depending on how dark this point is, you will have a different number. So this is just an example to show you what a digital image is, where, like I told you, you have a pixel count at every point. Now the brightness, you see these three images which you see over here, this is of the same object. This is of a cluster called Westerlin 2, right? And the first one which you can see is an image. There are different ways in which we try to observe images. So in astronomy, we do something which is called scaling. That is, now, for example, in this image, you almost cannot see anything, right? There's absolutely almost nothing you can see. So then we realize that in your, if you have a 16-bit computer with you, then there are different grades of brightness which are possible. You remember in this previous image, I showed you numbers, 14, 15, 256, whatever. But if you have a 16-bit computer monitor, then what you do is, this is the range which you have of brightness. That means the brightness value can be anything from 0 to 65,536, right? But like in this object, when I'm looking at just like this, I don't see anything. Why is that? Because if you actually, now if you take a scaling, that means you see to it that you only observe pixels which have a number between 4572 and 6002, right? Then in that case, you will be able to see this object like this. So this is the same image, just with scaling. Similarly, if I take the point, the value at every pixel, and I square each value, then it's called square scaling, and I get this. So what this is doing, this is enhancing the value at every pixel because it's taking the square of it, right? And therefore, this is called square scaling, right? And right. So this is what is called square scaling, where you can see that you can see these stars far better. So in astronomy, what we do is we have different kinds of software with which we can even enhance the colors. Yeah, there's a question I can see from Kush Thakur asking to interrupt. Why don't we see colorful telescope in Hubble and James Webb telescope than black and white? So like I told you, what is done is, for the image, you basically use filters. And when you use a filter, what you're getting is like a black and white image. But then when we want color images, we couple images which are in different filters. For example, in red, blue, green filter, we couple them together, and then what we end up is with a colored image. But otherwise, from our CCD, what we are getting is in principle a black and white image. So the colored image is in a way artificially produced, right? It is not the actual thing. We actually artificially produce it. And then the image can be further enhanced also by, for example, you look at the scaling. This was linear scaling. This is square scaling, right? You can scale it so that it enhances the properties of the image. Now here I'm showing you an image of another cluster which is called NGC 281. This is actually a Pac-Man Nebula. You can see various colors in this. It's a very beautiful colored image. And now I'll show you how do you actually get the colors in this image. So if this object, this is called the Pac-Man Nebula, if you were to observe it in optical, you will see it looking something like this. And why does it look like this? Because there's a lot of dust over here. There's a lot of dust over here, and dust, what it does is it absorbs light. So you cannot see light through the dust. So there's the dust over here due to which you cannot see what's behind the dust, right? And then here you can see this is some kind of nebulosity, some gas and dust which is around, which is partially absorbing light, partially re-radiating light. So this is how this looks like if you were to look at it in optical, right? But again, this would be an image which you take in more than one filter. The same thing, there's another telescope called Spitzer. If you actually look at it through Spitzer, Spitzer looks in infrared wavelengths. So in infrared wavelengths, infrared has the property that it actually lets you see through dust. Okay. What is false coloring? I'll just tell you what is false coloring. So what happens is that if you're looking in infrared, you can actually see through the dust. That means in the dusty regions where you could not see stars in optical, right? If you could not see stars in optical, you will see here, you do not see anything through this part, right? But if I see it through infrared, you can actually see more, because this is in infrared wavelengths, you can actually look through dust. And here's a better image of Spitzer, which is actually, look at the amount of stars you can see in this dusty region. And you can basically see these stars because you are looking at this in infrared. So in infrared, you have the property of, you are able to actually look through dust, right? Which you could not see in the optical image, right? Now the same area was observed by Chandra. Chandra is a telescope which actually observes in X-ray. Now in X-ray we know are short wavelengths, that is high energy. And therefore now, to answer your question, what about artificial coloring? So now this is the X-ray image of the same nebula, but because we know that X-ray is shorter wavelengths, that means it's blue or purple colored light, violet. Therefore, we actually put this blue color in it for this. So artificial color which we put for this is we put purple color, because we know that X-ray is basically short wavelength which will be purple or blue in color. Similarly, Harshavardhan is again asking me about different colors. So the different colors are detected based on the filter which you use to see it. That is what you're using for different colors. This does not take photoelectric effect into account, because the material that for photoelectric effect, you need a metal. This is not a metal because you are having a material through which light can pass through. Okay, so therefore in these detectors you don't have metal. For photoelectric effect, you need to have a metal which has extra electrons, so that if light falls on it, it can emit the electrons, right? But in this case, this is not a source of that kind. So in this case, this is a thing for which light can penetrate. But what we do is that because we know the wavelength of that light, so we know X-ray is shorter wavelength, so we say it's purple in color. Similarly, here when we are looking at infrared, we know this is more longer wavelength, so we give an artificial redder color, right? While for X-ray, we give a bluer color. Next, what we do is we overlay all these images and you get an image like this. So this image is basically a composite image. Behind what you have is the X-ray image, which I showed you previously. Sorry, this is the infrared image, right? And over this, what we are doing is we are putting the X-ray image. So look at this. This is the infrared one. Here's the X-ray one. And then when we add them all together, you can see these purple parts. So these purple parts are the X-ray sources in this region. These sources are emitting an X-ray. And the rest of this part, this redder part, is the part which is in infrared, right? So what we are doing is when we are making a composite image like this, we are doing this like that. KMR is asking me same concept for radio image. Exactly. That's exactly right. When you're doing X-ray images, radio images, and all of them, we artificially add color. Okay. We artificially add color knowing the wavelengths. So supposing if you're using 3 different filters, then generally what is done is that the filter with the longer wavelength is given the red color, while the filter with the shorter wavelength is given the blue or the violet color, right? So we artificially put red, green, blue, depending upon what is the range of wavelengths we are looking at, right? And then we do image processing. We can do various things of image processing to actually enhance the images or look at images in some way or the other, right? Okay. Now, the other kind of data I was talking to you was spectra. We already know what are spectra. That is, for example, when light passes through a spectrum, it gets separated into its individual colors, right? Which is the Vibgyor. And what we basically do, look at this thing. We basically look at the light and we basically see what is the brightness of this light in different wavelengths. So this is the wavelength which corresponds to red. We see what is the brightness and we say it's like this. We say this is the brightness in the blue color, this is the brightness in the green color. So the intensity we can plot via wavelength. The interesting part about spectra is that there are certain wavelengths at which you get what are called black lines. Okay, these are black lines in the spectrum. And this is what we call absorption lines. So these absorption lines are particular wavelengths which are absorbed, right? From the source, they are actually absorbed. And that is why you are seeing these black colored lines. Now, what's very important about these black colored lines is there's absorption from the source happening at certain wavelengths, right? And because they are at certain fixed wavelengths, they are characteristic of the chemical composition of that gas. For example, if there's a star which has made up of, for example, hydrogen, then you will see that the spectral lines which correspond to hydrogen, they are the ones which will actually show you either absorption lines or emission lines, right? So you will get absorption lines or emission lines in the spectrum depending upon what is the chemical composition of the material, right? So for example, it's a star. Depending on whether it's made up of hydrogen or helium or carbon, you will actually see the spectral lines. And that is very important because that is the way in which you will actually know the chemical composition of your source. So for example, if you want to say there's helium on the sun, helium was discovered first on the sun, yeah, the element helium, because helios basically means the sun. And how was that found out? Because if you look at the solar spectrum, you will see that the lines which correspond to helium, either you have absorption lines or emission lines, depending upon which part of the sun you are looking at. And accordingly, you can identify the chemistry. And therefore, spectrum or spectroscopy is very, very important in astronomy because that tells you the chemical composition of your source. See, in astronomy, your source is so far away that you cannot actually look at your source in you cannot get the chemistry of it, right? You can't put that material in a test tube and check what is it made up of. So the only way you can do that is via the spectrum, which is spectroscopy, right? And therefore spectroscopy is so important. Joseph is asking me what is one-dimensional data. So for example, spectroscopy, a spectrum is one-dimensional data because it's telling you the difference in intensity over wavelength. So that means if you're changing your wavelength, it's telling you what is the change in intensity. So it's basically moving at this dimension and giving you this. But for example, a digital image is two-dimensional data because you have a grid, a two-dimensional grid on which each point you have the pixel value, right? And therefore that would be an example of two-dimensional data. But a spectrum is an example of one-dimensional data, right? Ismat Jamil is asking me why in intensity versus wavelength, the line is broken at many points. So thank you. That's exactly what I was talking about, was if you look at the spectrum, right, you can see that here there's a dip. What does this dip mean? Is that there's a fall in the amount of light. So if you actually look at the spectrum, you see a black line. So what is the black line is because the light in this wavelength did not pass through, right? You could not see the light in this wavelength and therefore we had a fall in the brightness, right? And that is this line. So these breaks are happening at, these are what are called absorption lines. These are the breaks. If you had bright lines coming over here, white lights, those would be the lines which are what we call emission lines. But in this case, in the picture, what you're seeing is absorption lines. Okay. Now, in astronomy, what we do is just to make it more convenient. Okay, so KMR is asking me another question. The doubt is when we say calcium 2, does it mean singly or doubly ionized? So actually what happens in astronomy, we have a slightly crazy way of naming things. So what happens is, For example, hydrogen, if we say H1, hydrogen H1 is just neutral atomic hydrogen. Okay, neutral atomic hydrogen is what we call H1. If the hydrogen gets ionized, in the sense it loses its one electron, right? So in principle, its charge will be, it will become an H plus. But in astronomy, we call it H2. H2 is basically singly ionized hydrogen. So similarly, in that case, calcium 2 is singly ionized hydrogen. Calcium 1 is neutral hydrogen. Okay. So in astronomy, we have this slightly different way of nomenclature, where neutral is where we put 1. So if you say calcium 1, that is neutral calcium, or neutral hydrogen is H1. But singly ionized hydrogen is H2. So therefore, Ca2 will be singly ionized calcium. Okay. Alfred is asking me how space pictures captured except telescope. I didn't understand the question very well. Could you rewrite the question? Sambit is asking me, are the absorption line spectrum due to atmosphere of Earth, or it's a good? Okay, that's a very good question, Sambit. So actually, in principle, when we are looking through a telescope, you will have both effects coming. You will have the effect coming from the atmosphere as well as from the source, right? And therefore, what we have to do is we have to always correct for the atmosphere. Before we try to discover what is happening with the source, the first thing is we need to correct the spectrum for the atmosphere. So what we do is we specifically remove all the atmospheric lines. We know that what are the lines which we can get from our atmosphere, because we know the chemical composition of our atmosphere, right? Now we know it has water vapor, carbon dioxide, oxygen. We know the material, the chemistry of our atmosphere. We have to correct for our atmosphere, and only then will we know what is coming from the source. So Sambit, we have to correct for the atmosphere before you study the source. Okay, you have to do that. So what is done in astronomy to make it convenient is you actually make what are called data cubes. So supposing if you took images of the object in different wavelengths, so these are the blue wavelengths, the green wavelengths, and the red wavelengths, you can actually pack these together, you know, like a bread packet, like you put bread in a packet, you put all the slices one after the other. Exactly in the same way, you put all the slices one together in such a way that wavelength is either increasing or decreasing in one direction, right? And these are what are called data cubes. So in data cubes, we stack them all together like bread, right? And put them all together so that we can actually keep them all together. We know that they are of the same source, right? They are from the same source, and therefore this thing. Welcome, Sambit. Please continue asking questions on the chat. I'll keep seeing that. So please ask me questions while I'm speaking, right? That at least gives me, I'm convinced that there are people listening. Okay. Now let's move to the next type of data which we have, which is what is called catalog data. So I told you catalog data is data in the form of a table. For example, you have an object. You have in astronomy, we have coordinates which are called right ascension and declination. You could have galactic longitude, galactic latitude, and various other parameters. So this is in the form of a table. Okay. So this is what is called catalog data. Catalog data is data in the form of a table. Okay. And that's what's described over here. And the other type which I was telling you, the next type is what we call time series data. So like, for example, I told you have a source of light and its brightness. You can see the brightness of the source of light as this is my time. You see that the source became bright, then it became faint, then it became bright, then it became faint. So there is a difference in the brightness of this source. So for example, if you look at it from here, you can actually see how is this actually changing. So this is the time period. This is the time period which you have. And this is telling you how is it changing with time. All right. So that would be your time series data. So Joseph is asking me, in three-dimensional data, can we view the source in any angle digitally? No, you cannot, because you are looking at it like this. How will I know how does the source look from behind? Because I don't have data on that, right? I don't know what it looks like from behind. So I'm only looking from here. I can only see it from here. I cannot see it from behind, right? So I will not know that. Kalpana is asking me if we correct for water vapor in our atmosphere, aren't we risking correcting for water vapor in the source too? Yes. So so this is a tricky business of how do you actually correct for if the same element is there in this as well as that. So what is often done, the simplest way is you take data on source and off source, right? So for example, I take the spectrum of light of the source, means away from the source and width, and then I subtract that, right? So I know that in the sky so much is anyway there, and then if I have additional amount coming up, I know that's coming because of the source and not because of the sky, right? So there are ways of handling that. Like I told you, you take off source and on source data and you correct it, right? And with that you will know what is the difference. What is on the y-axis of Samit is asking what y-axis of time series data. So this is intensity, this is brightness, and this is time. So this is telling me how is the brightness changing with time. This is my time axis and this is the brightness axis. Ismat Jamil is asking me what is the possible reason that intensity is changing. Okay, so there can be many reasons why intensity is changing. The star could be a pulsating star. It's increasing, decreasing in size. It could be that the star has a planet which is going around it, which is causing a change in difference. So there could be many sources of why. And there are different ways of trying to understand or study that to guess what is the source of the change, right? There are ways of actually doing that. And so depending upon how, this is called a light curve. Depending on how the light curve works, I'll be showing you all an example. You actually use that to understand what is happening. Now there are various tools which are used in astronomy to study these things. There is a tool called DS9 which is used for image visualization to look at images. This is DS9 is from Deep Space Nine. Okay, most astronomers are very strong science fiction lovers. Catalogs are handled using a software called TopCat, which is very easy to understand. You can also use programming language like Python. And they are not to be used like black boxes. You have to understand how does the software work so that you can actually use it, right? Now with all this data, there's also what is called metadata, which is also very important, which is about the data you are studying. It will tell you things about it. For example, which is the telescope which was used, what was the exposure time, what were the filters used, what is the, various things about the data. That's called metadata. Now we'll move a little ahead. Sadanand is asking me, can light bend in space? Yes, it definitely bends in space depending on the masses of the object. So a very massive object will bend light very strongly, but even a low mass object in principle bends light. But obviously the bending is a very small quantity, which is very difficult to measure. But there are cases in astronomy itself where we can see very well the bending. And the interesting thing is, in astronomy, we have what is called gravitational lensing, where you actually have a very massive object which actually bends the light in such a way that the light, it actually acts like a lens, right? So what do lenses do? Lenses basically bend light, right? And this, what it basically does is it bends light. So you actually see lensed images of galaxies. So you have a kind of a lens, gravitational lens in the front. So the galaxy which is behind it, you'll actually end up seeing, multiple images of that galaxy, or you'll see arcs, or you'll see various kinds of artifacts coming up, basically because you have a gravitational lens sitting in front of that object which is creating this, right? So yes, it will do it. So Ashish is asking me, how do software like Stellarium work, that too offline? How is the data organized? So Stellarium works, it basically works online. According to me, it does not work offline. It works online. It has a certain amount of material stored with it. And with that, it basically matches it to star maps. But if you're running it offline, probably you already have the downloaded star maps. Then it can do it can actually tell you what's lying in the sky. So then in that case, you could probably run it offline. Right. So I'll proceed ahead. You please continue with your questions. So
Hello. Hello. Hello, madam. Hello, madam. Hello, sir. Kulkarni, sir.
What happened? What happened? I don't know either. I'm on here.
Yeah, madam, sir, I think network problem with the madam.
Where did she go?
One second.
Maybe.
Arvind sir,
Yes.
yeah, there is some technical problem. She may need 5 minutes, so you
Right,
can
right.
engage.
Sure.
Yes, sir.
Go ahead.
Sir, Arvind sir, you
Yes,
can
yes.
engage for 5 minutes, sir.
Yes, fine.
Yes.
Well, as it goes, there is some technical problem. We will address that. Until then, I just want to continue saying that there's a lot of information we are getting. In fact, I did astronomy observation through telescopes some 30 years ago, 30 or even 40 years ago. The techniques were different. The methods and these things were same, but the techniques were different. The technology has increased in a very different direction. So to be able to interpret the data, it is necessary to understand how the data comes in and how it gets connected. I think Dr. Priya is back, and I will also withdraw.
Yes,
from
sir.
my, yeah.
Thank you, sir. I'm back. Yes, I'm back. So I was talking about Astronomy Archives, and this business of actually making Astronomy Archives has been done since a very long time. People have tried to actually make Astronomy Archives, and what you can see is that so the earliest archives were made by Hipparchus, by Tycho Brahe, and actually the first example of using of astronomy archival data was used by Kepler. So Kepler, when he actually studied planetary orbits, he wanted very detailed observations of the movements of planets, right? And there were very good observations made by Tycho Brahe. And that's exactly what Kepler used to find out his laws of planetary motion based on the data of Tycho Brahe. So that would be one of the earliest examples of effective use of archival data to actually get science out of it. So that's what Kepler did. And then you had a lot of people cataloging, observing, cataloging things. So you have what is called the Messier Catalog, where objects are mentioned, are cataloged as M1, M2, M3, M4, etc. You have the NGC, the New General Catalog. And in that way, since a long time, astronomers have been organizing data so that it can be in a certain form to be used. Now, one of the earliest data sets we have is the Palomar Sky Survey. And this was actually in the 1950s, where actually the Schmidt telescope was used to actually, this is the one, which was actually used at Mount Palomar to actually get data. And they had a whole set of about 2000 photographic plates. Okay, this was a time when photography was, this is pre-CCD. And therefore, they actually had photographic plates where they had photographs. And later on in the 1990s, these photographic plates were digitized. In the sense, they scanned these photographic plates and actually get this data. I can see another question from Kalpana. LIGO strain data would classify as time series. Yes, that would classify as time series because you're actually looking at the difference coming with time, right? So yes, you will actually get it as that. Okay. So that was the times of Palomar Sky Survey. So if you actually look, you will find this. This is called the DPOS, the Digital Palomar Sky Survey, where you can actually find it in digital form. This is just by scanning the photographic plates. And then comes in technology where you have charge coupled devices, which I was telling you about, which are there on all our cell phones, on all our laptops. You're seeing me because of a CCD on my laptop. And therefore, there's a very fast increase or rise in the way of technology in which people could actually do it. And hence there are a whole bunch of citizen science projects which people can do, which are even without any knowledge of science, where you can actually do it. Joseph Gerald is asking me, can we get some data on particular source detecting gravitational waves? So in principle, like is the spirit of science, you see all the gravitational wave data which has already been analyzed, it's all available. So you can actually, it's all available on the net. I do not know the actual website. It can be found out, but in principle, it is all available online. So what is done in the system of astronomy is that if I make observations on the basis of which I make some, I find out something, what I do is I also keep the data available to anyone so that anybody can analyze that data and get the results which I got, right? And if a person wants, he or she may even try to analyze that data in a different way to get some other results. So in principle, for gravitational LIGO data, it's all available online. You can get it online. Somebody raised a hand, right? Okay. So I was telling you all about CCDs, and CCDs is obviously the way which we now use in astronomy to actually get our data, because in this case, these are what are called linear detectors. That means as you go on exposing the CCD, it goes on giving you counts as increase. If you know on a photographic plate, initially it's linear. After some time, as it gets exposed, and then even if you expose it to any amount of photons, it will give you the same amount of values, right? So we don't have the time, but in short, the CCDs are very specialized in the sense that the pixel count can give you a very good estimate of what is the amount of photons which fell in a certain region. And similar things like CCDs are even there in other wavelengths. For example, in X-ray, also you have something similar to CCDs. There are counters, okay, proportional counters, etc., which are used to measure in X-ray and get the data in that way. Yeah, so Kshitij is asking, what is a CCD? A CCD is a charged coupled device. So a charged coupled device is what we get all this digital data from. So what I told you all in the beginning was it's like an array of buckets where you are actually counting the amount of light coming in a source. So it's basically an electronic device, and hence it's called a charged coupled device, a CCD. Okay. So in that way, we have similar things in other wavelengths, which can actually give you digital images in the case of X-ray, radio, in various wavelengths, right? Now over here, you can see is that along with this, there's a lot which has happened in technology. And the best part about Astronomy Archives is that it's in a true spirit of science, where Astronomy Archives are available to everybody. And in the beginning, what happens is, for example, if JWST, right? In the beginning, you'll have certain data which is only for the instrument groups because they are still fine-tuning their instruments. But they definitely always will give a certain amount of data freely to everybody to use. So there is a certain amount of proprietary period when it is owned by someone, but after a certain time, it becomes free to all. And based on that, there are various citizen science projects. For example, there's something called Galaxy Zoo. There's a project called SETI. There are various projects which are done in which, because the data is available freely to everyone. Okay. So somebody is asking me what kind of data is available for black hole images. So in principle, obviously you cannot image a black hole, right? Because the black hole absorbs light, even light cannot escape through it. And therefore, what happens is you do indirect observations, and often the indirect observation is in X-ray. So for example, people may actually observe the thing in X-ray and observe that and try to see what is the kind of, what is the, what is happening in the neighborhood of the black hole to study the black hole. So black holes are basically studied by indirect observations of objects near black holes. So that could be in X-ray, that could be in infrared. For example, the supermassive black hole in the center of our galaxy, we observe that by infrared observations, right? So this will vary. Now there are various places where this data is kept. Okay, wormholes, no, they have not yet been detected, Joseph. Okay, so here I've given you a whole list of different data archives. I will later on share this presentation with Sir so that he can share it with you and you can see all these different sources of data. And you have to go to their individual websites to actually find them. Now, for example, let's start off with the first example. This is the Hubble Space Telescope data set. So the Hubble Space Telescope is a separate website where you can actually get all the data from the Hubble Space Telescope, from the James Webb Telescope as it comes. There's what is called the TESS Exoplanet Survey. There are various surveys which you can get from the Hubble website. So it has various things, like I told you, it has data from Hubble, Kepler, and some other missions like Galax, Fuse, etc. And you can use various virtual observatory tools. We don't have time to talk about it, to actually look for images, spectra, catalogs, various things which you can get from it. And there are various things available on these websites. Another very important data set. Yeah. So if you actually see that there's another very important data set, which is the data set of Gaia. Gaia is a European Space Agency satellite. And you can see that this is also giving data on its website. There is also, so Krishna is asking me that he heard that Stephen Hawking said that black holes are not so black. It means at very small range. Yeah, but that is those are quantum fluctuations. So actually observing that, at least in present times, is not possible. We don't observe that at present. It is something very small. Okay, those are going to happen by quantum fluctuations, which are going to be in a very small brightness, very small amount. So we can't detect that at present. India has another telescope called the GMRT, which is the Giant Meter Radio Telescope. And that also has its archival site, which is available online, where you can actually see the data from it online. There is the X-ray observatory called Chandra. Chandra also, you see this is Chandra Data Archive. So if you look online, you can actually go to this and see the Chandra archive, and it will give you various data sets from Chandra. This is what is called the Sloan Digital Sky Survey and the SDSS. This is also data set which is actually surveyed the sky in 5 wavelengths and using this telescope, and it's available online and free for everyone. Yeah, so Krishna is asking me, what are quantum fluctuations? So the thing is that we know that, like you said, black holes are not so black, but there's a finite probability of it giving out a small amount of, small amount of radiation, right? So that would be of the it would be like, so it would be just by quantum physics, that there will be a certain variation in the position and momentum of objects, right? And that is why, and that is a very small amount. That is the amount which is h bar, right? Delta x into delta p greater than or equal to h bar. And h bar is nothing but Planck's constant, which is 6 into 10 power minus 34 joules second. So that's, in short, a very, very small quantity. Okay. So just think of quantum fluctuations as a very small quantity. And that's why I said it's very difficult to detect, and we cannot detect it, right? So, so let's just talk, finally, I'll talk about some of the possible projects which one can do with astronomy data. So there are a whole bunch of citizen science projects, and these are basically projects for which you do not need to know any science. You do not need to know any analysis. Without knowing that, you can do some amount of analysis. For example, there's a project on asteroid searching, looking for asteroids, using a software called Astrometrica. There is a project on looking for planets called Planet Hunting. There's one on classifying galaxies called Galaxy Cruise. There's on exoplanets. There are various citizen science projects which actually people can participate in. And to observe exoplanets, there are basically 2 NASA telescopes. These are both telescopes in space. One is called Kepler and the other one is called TESS. Okay. So exoplanets are what? These are planets which are outside our solar system. So if you want to look for life outside, other than Earth, you look for planets outside the solar system. And you may be aware that 2 years back, the Nobel Prize in Physics was actually awarded to Michel Mayor and Didier Queloz for their discovery of the first exoplanet. This was 2 years back, 2019, when they got the Nobel Prize for detecting this. And so therefore, this has been something this was actually detected in 1995. So you see that since a very long time, people have been actually looking for exoplanets, that is planets outside our solar system. And they are detected using various methods. One is by using the radial velocity. One is by using a technique called microlensing. One is using a technique called transit photometry. And one is using a method called direct imaging, right? So there are various methods in which we actually look for exoplanets. So this is the transit one that, for example, somebody asked, how does the brightness change? So for example, if you have a planet of the star going around the planet, then as the planet is dark, the planet is not radiating. So as the planet goes in this thing, the light from this star will dip. Okay. And this is the light curve of a star when the planet transits it, right? So what Kepler does is it actually looks at exoplanets to actually look for light curves. And it looks for light curves if you have dips, so that it can use these dips to then detect whether there are planets, right? But the problem is that this dip, if you look at this image, you'll see that this planet is so small compared to the star. And therefore, this dip in brightness here looks big to you, but actually this dip is a very small quantity. It's barely a 1% dip, right? So you need very accurate measurements so that you can detect this 1% dip at a certain periodicity. And then people do very detailed analysis of this so that they can find out, for example, how many planets are there, what is the sizes of planets, what is the orbital period, what's the inclination. So here you can see another example. So I'll just show you 1 minute. I'll just show you this. Sorry. So this is a very detailed kind of analysis one can do using Kepler or test data to find the parameters for the planet. Another way is, this is a method which is called microlensing, that if the planet comes in front, because of gravitational thing, you'll have a slight increase coming in the brightness of a star. And this is what is called microlensing. So again, you look at the light curves of stars and you look for this kind of a microlensing signature. So typically what happens, you'll get a brightness coming up like this. This is the planet, and you'll have this brightness coming up like this. And you use this curve to actually get parameters of the planet. So the Kepler mission is basically dedicated at only looking at a very small part of the sky. That part is literally a fist at arm's length, that much of the sky. And it just kept looking at that part and looking at the light curves of all the stars. Yeah, there are many stars in this region, and it kept looking at them. After a certain point, there was a certain problem with Kepler. There was one of the reaction wheels which, had a failure, and therefore there was a phase 2 of Kepler called the K2. And in K2, again, Kepler looked for another set of sources for more than 150,000 stars, looking for transiting exoplanets. So all the K2 data is also all available, which you can analyze to actually look for planets. There is also the TESS satellite, which is the Transiting Exoplanet Survey. And again, the TESS data, it was launched in 2018. And you can again do light curve analysis of the TESS data. You can do light curve analysis to get the masses of the planets, the radius of the planet. Because you get mass and radius, you can also find out the density of the planet as well as the temperature. So there are various Kepler targets for which you can find out the thing. So what you do is you have this curve and then you kind of fold it, right? You repeat it so that you get more points and fit it to get parameters. So that's the kind of projects one can do with exoplanets. The other kind of projects one can do is, for example, with globular clusters. You can use this using HST data, Hubble Space Telescope data or Gaia data. And you can actually use this tool. This is software, so we don't have time to show you, but this is what is called an aperture photometry tool. So you basically look at the globular cluster, and this tool, what it does is it actually looks for a source. This will be the brightness in the source, and then it looks for a region which is outside the source. So between the green and yellow line, you are outside the source. Within the red circle, you are inside the source. So you know the source and outside the source, you subtract the two, and you can get the brightness. So what happens is, here's your star, and this is the outside part. This is the gap. You do this, and this is what is called aperture photometry. You know the inside, you know the outside. You subtract the two and get the brightness of your star. Using this, we get the brightness of all stars, for example, in this globular cluster. And then what can be done is one can plot what are called color magnitude diagrams. We don't have the time to do that today, but essentially for that, you need the brightness in two filters. So on the y-axis, you plot it along one filter, and on the x-axis, you plot it in the difference of two filters. And you plot what are called color magnitude diagrams. So we can actually plot these color magnitude diagrams once you've done the photometry. Ashish has a question: how to use the light dip graph of an exoplanet for research work. So there is a technique to do it, which will obviously take time. It would at least take 2 hours to explain how to do it. So I can't be doing it today, but in principle, it can be done. It is done. It is done by people. So these are color magnitude diagrams, which you can plot once you have the photometry. By photometry, we mean to say the brightness in certain filters. You can also study what are called stars or star clusters or stellar streams using Gaia. If you remember, I showed you what was Gaia, and Gaia data can be used to study any of these kind of objects. So in this case, you will have what are called catalogs, and the catalogs can be analyzed using this software called TopCat. TopCat is a tool for operation on catalogs and tables. So you can use TopCat to actually get this. And there are ways of analyzing the data. We don't have the time for that today. But essentially, you can use this to query the data, get the data, and to plot it. And because all these stars are moving with the same velocities, you can identify where is the cluster. The cluster is the set of stars moving with the same velocity. This is around 0, 0. These are non-zero, and this is the cluster. And you can actually use this to find out the distance, which is 1 by parallax, and plot that and get various parameters of a cluster. Right? And you can actually plot the cluster and look at. So you actually see a cluster of stars. You'll see all these stars, the blue ones, moving with the same velocity in the same direction. And all of these are members of what we call the cluster. The remaining pink dots are stars which are moving in other directions, and hence they do not belong to the cluster, that same group of stars. So now you can find a cluster and you can study the membership of the cluster, which of the stars are members, using various techniques, distance photometry, spectroscopy, etc. And we use this to actually plot that color magnitude diagram, which I told you, or it is also called in astronomy the HR diagram. Okay, so we can use this to actually plot the HR diagram. And when we plot the HR diagram of clusters, we can actually find out the distance to that cluster using what is called the distance modulus. Right? I'm sorry, we don't have time to go into details. Each of these things would take a lot of time, and we can actually plot the HR diagrams. And these are actually used to find out the ages of clusters. So if you plot the HR diagram of a cluster, you can actually find out the age of a cluster. You can also use archival data to look at external galaxies. That is, for example, galaxies other than the Milky Way, the one that we belong to, from Hubble or various data sets or SDSS. You can find data of external galaxies, of other galaxies. Yeah, so Sambit is asking me, how do we know the distance between the source and the Earth? So with Gaia, we have what are called parallax measurements, and the distance is 1 upon parallax. So from the Gaia data, we know the parallax to a particular star, and 1 upon parallax is the distance. So that's how we have the distance. So if you're observing different galaxies, you can do, for example, study the morphology of a galaxy. This is a certain software called GalFit. In GalFit, if you look at a galaxy, you can actually build a model galaxy which is made up of this galaxy. And if I subtract this from this, you can get this, which is a residual, through which you can actually see that this galaxy is a spiral galaxy. Otherwise, you would have not noticed that it's a spiral galaxy. But when we take this residual, you will notice that this is clearly a spiral galaxy. So there are various things you can do with observations of external galaxies. Santosh Kumar is asking me, our nearest galaxy, that's Andromeda. That's Andromeda, which is the nearest galaxy to us. And there are a whole bunch of still more projects, which I won't talk about today, but there are projects which one can do studying gravitational lensing, for example, which I was talking to you about, where you'll have multiple images coming because of gravitational lens, right? And you can also have studies of dark matter and various kinds of projects which one can plan based on the amount of archival data available. So like I hope I've convinced you in this 1 hour that essentially there's a lot of archival data available, and depending upon your object of interest, you can actually pick up the projects or thing that you want, right? Sambit is asking me, are there other methods to know the distance between two cosmic objects? So in principle, there are other methods. I don't have the time to talk about it, but yes, there are other methods of finding out distance other than parallax. There's one, for example, called standard candle. You know what is the general brightness of a certain kind of a source, and then you see it at a certain brightness. So you know how much the brightness has diminished, and you can use that to actually estimate what is the distance to the source, right? Because you know the diminishing amount. So that can be done. So I will just conclude with this, that the world is always open, waiting to be discovered. There is a whole set of archival data, astronomy archival data, that is available on the internet. like I said, ranging from studies of exoplanets to stars to external galaxies to our galaxy also. And it's just waiting for you to be trying to analyze it or discover it, because obviously the amount of astronomical data available is much, much larger than the amount of astronomers we have. And therefore, it is very essential that people actually look for it. Kalpana is asking me, are there spectroscopic data? Yes, there are many spectroscopic data sets also. It just depends upon which object spectroscopy do you want. Do you want it for stars or galaxies or exoplanets, or what are you looking for? But they are there. There are many spectroscopic data sets also available, right? So there's a question from Kalpana. What is simulation data like? So what happens in astronomy is we do not have the pleasure of touching our sources, right? Like in a lab, you can actually take a pendulum, you can, do the pendulum, measure the time period, change the length of the pendulum, and do things like that. But in astronomy, we do not have that kind of freedom, right? And therefore, what we do is simulate. So for example, like the same example which I gave you, for example, of a pendulum. Supposing you want to change the length of the pendulum to actually look at what is the difference in the time period, right? And maybe you have analyzed and discovered the equation for time period. You say time period is root of 2 pi root of L by G, right? So therefore, what do? You create a simulated pendulum where you can keep on changing the value of L, and you use the calculation which you had used, 2 pi root of L by G, to actually define its time period, right? So in that way, you are simulating a pendulum without actually doing it. In astronomy, what happens is that since we do not touch our sources, or we do not get the freedom to change anything with our sources, what we do is we make simulations. And for example, if you had a simulation of a pendulum and you are observing a pendulum, then your simulation will tell you that if you're getting a certain time period, what is the length of that pendulum, so that you can get that kind of time period. So that answer is answered to you using your simulation. So you use your simulation to understand observations and your theory. What was the theory? How did you derive your formula 2 pi root of L by G? You use theory to do that. And therefore, when you observe a pendulum, you compare that with the observations of your simulation, so that you know whether your simulation was correct or wrong. For example, if you wrote 2 pi root of L cubed by G, and then you notice that your simulated value is not matching with your observations, right? Then you realize that something is wrong in your theory. So you say, oh, it should not be root of L cubed by G, it should be something else, right? And then you try to discover what is the correct answer. So that's why in astronomy, we use a lot of simulations, so that we simulate circumstances, and we use that to actually interpret the observations or the theory which we have, right? So, yeah, so Fahim Andrabi is asking me for another webinar on research methods and software. So actually, yes, that can be done, but there are there are many research methods and many softwares which are used in astronomy and astrophysics. So there's not one, there are many. So for example, if you're just dealing with TopCat, you will take probably 2-3 days to train somebody on how to use TopCat, or 1 day to how to use DS9. But yes, I am sorry I could not talk about them in detail because there are so many of them. But I just wanted to give you all a feel of what are the things available. Then you can one by one try to study each of them depending upon what kind of projects you want to do and what are the things that you want to study, right? So thank you so much. Thank you, sir. Arvind, sir.
Dr. Rajesh,
Yes.
Dr. Rajesh, can I speak for half a minute again?
Yes, sir.
Yes, sir. Yes.
I just want to say that what Dr. Priya did was she invited us for a wonderful lunch, but all she ended up doing is showing us about 100 dishes. Now, what do you do with 100 dishes? We can't eat 100 dishes at the same time. We can only see 100 dishes, and then she goes away without serving any of the dish. She says that, look at my 100 dishes here in the kitchen, and if you have time, eat it. If you don't have time, get lost. That's what.
No, but sir, I don't know what is it that you like, right? I don't know whether you want to have.
So to decide what I like to do in the 100 dishes that she is offering, I need to know what those 100 dishes are.
Yes.
Okay. Coming to the Krishna's Chappan Bhog, Sri Krishna wants 56 dishes every day, and there is a mathematics for it. Actually, for 8 days, he was put in a jail or something, and then every day his mother, Krishna's mother, needed 7 dishes to be cooked. So he needed 56 dishes once he comes out of this kitchen jail. So something like that is happening here. What Dr. Priya did to us is she had shown hundreds of dishes, and now it is our duty to pick up the best that is available. For that, we need to do a thorough. We need to understand what exactly we need, and then you go for the dishes that we need to do. Obviously, as some student asked there, Fahima, somebody, that we need another seminar. But before that, I suggest that people should summarize what they have learned. And now that they're exposed to a huge amount of data from various sources, now, by the time of June this year itself, the James Webb Telescope is going, and it is going to send us at least some 500 times more data than it is available. And I really don't know what we are going to do with it. So we take this opportunity to make ourselves ready for the next 3 months as the 18 mirrors are getting aligned using the laser beam, and use these 100 days or 3 months of period, so that before June, we will be ready to use the data. That's all I want to say. And then I'll hand over to Dr. Rajesh. Thank you.
Yes, sir. Yes.
Yeah.
So myself, Dr. Rajesh Nairi, convener and assistant professor of physics at PC Jabin Science College. So I take this opportunity to propose a vote of thanks. So on this occasion of a national level seminar on astronomical data, sources and analysis organized by the Department of Physics. I would like to express my sincere thanks to our beloved principal, so Dr. L.T. Horkeri sir, for his constant support as well. So I like to extend my sincere thanks to today's resource person, Dr. Priya Hassan, so assistant professor, Department of Physics, Maulana Azad, National Urdu University, Hyderabad, for spending her valuable time with us. So this was the program. So with the help of I think Dr. Arvind Kulkarni sir, we have planned. So very short communication, even with a very short communication, so we could able to get such a wonderful resource person. So thank you very much, madam, for accepting our request and so giving such a wonderful talk. So we have planned so many programs through this platform. So I think with the help of Kulkarni sir, so probably in April or so in same time, end of April, we are going to organize so seminar also, so related to astronomical data and analysis related things. So thank you, madam, for spending your time so with us and giving such a wonderful talk. Thank you.
Welcome, sir. Thank you, sir. Thank you for inviting me.
Yes. So I should remember one person who is actually, because of him, all these things is happening. So that is Dr. Arvind Kulkarni, so former director, SP Planetarium, Vadodara, Gujarat. So thank you very much for giving us such a wonderful platform and connecting all astrophysicists to our PC Jabin Science College. So we are extremely thankful to you, because this is the one area we are lacking. Mainly we have most of the events last 2 years. So we have conducted focused more on nanomaterials. Even we touched about zero dimensional material and quantum computation also, but we are not able to conduct even a single program connected with the astrophysics, because we don't have any contacts, so related resource person contacts. That is why. So because of we could able to connect that area also. So from our college and department side. So thank you very much, sir. So At last, I extend my sincere thanks to all faculty members, department faculty members, as well as participants. So for their active participation, so we could see so many questions. So most of the participants, so particularly our college participants, so this is a new area. So nowhere they are studying in curriculum, but in NEP we are going to put so separate paper on astrophysics. So that is why. So even then they are interested and they are interacting with the resource person. So I thank all participants for their active participation. Thank you one and all. So definitely, as the requested by the participant, we will conduct many number of programs connected with the astronomical data and the sources, analysis, all these things. Thank you one and all.
Thank you, sir. Thank you. Bye-bye. I have shared the link to my YouTube channel where actually there are lots of lectures on using things. So people who are impatient, who cannot wait till the next session, you can actually find it on YouTube. My channel is named Priya Hassan only, and there are different playlists with different, description of projects. So you have a look at that. Thank you, sir. Thank you.
Okay, thank you. So we will send feedback link.
Yes, sir.
We will send a feedback link in chat box. So please give your valuable feedback. So that will help us to conduct more number of programs. Thank you one and all.
Okay, sir. Bye-bye.
Yeah.
Namrata.